Matter falling onto a dead star can create some of the most extreme cosmic weather in the universe, and now, astronomers have finally captured a detailed look at what is happening right next to one of these stars. Imagine peering right down to the surface of a dense stellar corpse and actually mapping how hot, violent gas slams into it. That is essentially what a new study has done for a white dwarf system called EX Hydrae. And this is the part most people miss. These findings are not just about one weird star, they feed directly into how scientists measure distances across the universe. IXPE provides a new inner view. Astronomers at MIT used a space-based X-ray telescope to map key structures in the very innermost region of a binary star system, an area so energetic that most instruments have never been able to study it in detail. In an open-access paper in the Astrophysical Journal, the team describes how they used NASA's imaging X-ray polarimetry explorer, IXPE, to observe an intermediate polar system known as EX Hydrae. In this system, a white dwarf, essentially the exposed core of a dead star, closely orbits a larger companion star, forming a compact pair whose behavior can only be fully understood through high-energy observations. An extreme binary, EX Hydrae. EX Hydrae lies about 200 light-years from Earth, relatively close by cosmic standards, which makes it an excellent laboratory for studying high-energy astrophysics. In this system, the white dwarf has a strong magnetic field that pulls gas off its larger companion, funneling this material into a swirling, spiraling structure called an accretion disk around the white dwarf. Because this setup forms what astronomers classify as an intermediate polar, it is known for producing complex, intense radiation, including bright X-rays, as gas from the companion star crashes down onto the white dwarf surface. Surprising X-ray polarization. The researchers measured a surprisingly high level of X-ray polarization from EX Hydrae, where polarization describes how the electric field of the X-ray waves is oriented in space. Along with the high degree of polarization, they also found that the polarization direction itself was unexpected compared with standard theoretical models for this kind of system. These precise measurements let the team pinpoint the origin of the X-rays to the innermost region of the system, extremely close to the white dwarf surface, rather than from more distant or diffuse structures. A towering accretion column. From the data, the team concluded that the X-rays are produced in a tall, narrow column of superheated material pulled off the companion star by the white dwarf's magnetic field. This accretion column is estimated to rise roughly 2,000 miles above the surface, about half the radius of the white dwarf itself, making it far taller than what prevailing theories had predicted for such systems. That kind of discrepancy is a big deal. It suggests that the standard models of how matter flows and shocks in intermediate polars may be missing important physics, such as how magnetic fields shape the inflowing gas. Reflections from the white dwarf surface. The study also demonstrated that some of the X-rays do not travel straight out into space, but instead bounce off the white dwarf surface before escaping. Physicists had proposed this reflective effect in the past, but it had not been firmly confirmed in an actual system like this. The combination of polarization strength and polarization direction gave the team a way to distinguish direct X-rays from those reflected off the surface, providing compelling evidence that this reflection is indeed happening. X-ray polarimetry comes of age. Taken together, the results show that X-ray polarimetry is a powerful tool for probing high-energy environments around compact objects such as accreting white dwarfs. In practical terms, it means scientists can now map the geometry of gas flows and shock regions very close to the star regions that are otherwise too small and bright to resolve with ordinary imaging. But here's where it gets controversial. If X-ray polarimetry continues to overturn standard models, astronomers may need to rethink some long-accepted assumptions about how matter behaves in strong magnetic fields around compact stars. New window on accretion geometry. The team demonstrated that X-ray polarization measurements can reveal the detailed geometry of the white dwarf's accretion region, including how gas is funneled and where it finally crashes down. This geometric X-ray map opens the door to studying other accreting white dwarf systems that were previously too small or too complex to decode, especially those that had no clear predictions for how their X-ray polarization should look. In effect, X-ray polarimetry adds a new dimension to standard X-ray observations, turning what used to be a simple bright point in the sky into a structure that can be modeled and tested. The team behind the discovery. The work was led by postdoctoral researcher Sean Gunderson at MIT's Kavli Institute for Astrophysics and Space Research, who headed the analysis and interpretation of the IXPE data. His MIT collaborators include graduate student Swati Ravi and research scientists Herman Marshall and David Hunamorda, each contributing expertise in X-ray data, modeling, and interpretation. The study also involved a broader collaboration: Dustin Swarm from the University of Iowa, Richard Ignas from East Tennessee State University, Yoel Nays from the University of Liege, and Pragati Pradhan from Embry-Riddle Aeronautical University all played roles in modeling, data analysis, and theoretical context, reflecting how complex high-energy astrophysics has become a team effort. Light, fields, and polarization. All forms of light, whether visible light or X-rays, are shaped by electric and magnetic fields. Light travels as waves that oscillate at right angles to the direction of motion, and in many environments these oscillations can be oriented randomly. When light scatters off a surface or passes through certain environments, the oscillations can line up preferentially in one direction, making the light polarized. This is similar in spirit to how polarized sunglasses work. They block light vibrating in certain directions and transmit light vibrating in others. Why polarized light matters. Polarized light carries clues about where it came from and what it interacted with on the way to us. By measuring how strongly light is polarized and in what direction, scientists can infer the shape, orientation, and structure of the region that produced it or scattered it. In systems like EX Hydrae, this means polarization can reveal how gas is flowing, where shocks form, and how the white dwarf's magnetic field is shaping the incoming material, even though those regions cannot be imaged directly. IXPE, a new kind of X-ray observatory. NASA's Imaging X-ray Polarimetry Explorer, launched in 2021, is a specialized space observatory designed to measure polarization in X-ray light from some of the most extreme cosmic environments. Circling Earth in orbit, IXPE collects and analyzes X-rays from objects such as supernova remnants, black holes, and neutron stars, focusing not only on how bright they are but also on how their X-rays are polarized. This makes IXPE fundamentally different from earlier X-ray telescopes that primarily measured brightness and spectrum, giving astronomers a richer, more diagnostic view of high-energy processes. First, polarization measurement of an intermediate polar. The MIT-led study is the first to use IXPE to measure polarized X-rays from an intermediate polar like EX Hydrae. Even though intermediate polars are much smaller and less massive than black holes or full-blown supernova remnants, they are still powerful X-ray sources fueled by intense accretion. That makes them a kind of missing link in high-energy astrophysics, not as extreme as black holes, but still extreme enough to test how accretion and magnetic fields interact. But here's where it gets interesting. If systems this small already show such strong polarization, what might that imply about similar processes in larger, more energetic systems? Seeing more than a point of light. Many telescopes see intermediate polars as little more than unresolved points of light, offering limited information about the inner workings of the system. By considering how much polarization would be enough to decode what is happening close to the white dwarf, the researchers were able to design an observation strategy where even modest polarization signals could reveal the underlying geometry. The fact that EX Hydrae showed a stronger polarization signal than expected means the system practically lit up in IXPE's polarimetric view, providing much more detail than earlier observations. Magnetic fields and system classification. An intermediate polar is defined largely by the strength of the white dwarf's magnetic field and how that field governs incoming material from the companion star. When the magnetic field is very strong, the gas does not form a full disk. Instead, it is captured and funneled directly down to the star's magnetic poles along magnetic field lines. When the field is much weaker, the gas can spread into a more conventional accretion disk, gradually spiraling inward until it settles onto the white dwarf surface. A hybrid accretion pattern. In intermediate polars, the actual accretion pattern is more complicated and falls between these two extremes. Theoretical models predict that gas initially forms a partial accretion disk before the white dwarf's magnetic field grabs the inner part of that disk and channels it toward the magnetic poles. This creates a hybrid structure where some parts behave like a disk and other parts behave like magnetically controlled streams, making these systems particularly rich targets for polarization studies. a high-energy fountain and accretion curtain. The white dwarf's magnetic field is expected to lift material